Hey everyone, and welcome to another deep dive with us. Today we're going to be looking at something pretty interesting.
Yeah,
It's going to be in the world of number theory,
that's right, number theory.
but we're going to be approaching it through a lens that you might not
You might not expect.
expect. Yeah, we're going to talk about
From necklaces, exactly.
So get ready to discover how these simple adornments can unlock some really mind-blowing mathematical concepts.
Yeah, you know, it's amazing how something so commonplace as a necklace can have such intricate mathematical ideas behind it.
I know, right? It's really cool. And our guide for this adventure is going to be the online encyclopedia of integer sequences.
Ah, the OEIS.
The OEIS,
Yeah.
for short.
Yeah.
And it's like a massive digital library. But instead of books, it's filled with these fascinating number sequences, and each one of them kind of represents a unique mathematical concept.
Right.
And today we're going to be focusing on a sequence called A00000046.
Okay.
And this sequence dives into the number of unique necklaces you can create with a given number of beads. But there's a twist. We're not just stringing beads together like,
Right.
haphazardly or whatever.
Yeah, we're going to be exploring something called primitive necklaces.
Okay, primitive necklaces.
Yeah.
So what exactly makes a necklace primitive? It sounds like there's some rules that we need to follow here.
Yeah, you got it. So imagine you're making like a beaded bracelet, right? A primitive necklace is like a unique bracelet design that you can't make by just repeating the same small section over and over and over again.
Yeah.
See what I mean?
Okay. So it's like a fundamental pattern.
Exactly.
Something truly original.
Yeah.
So like a necklace with arsenated red and blue beads wouldn't be primitive if you had more than two beads.
Precisely because it would just be the same red-blue pattern repeating over and over and over again.
Okay.
And there's one other little rule that we're considering here, and that is that we're considering necklaces that are mirror images of each other as being the same.
Wait, so if I flip a necklace over, it's considered identical to its original form.
Yes.
Why is that?
Well, it all boils down to this concept of chirality in mathematics.
Okay.
So some objects are considered the same as their mirror image, and our necklaces fall into that category. You can think of it like your left and right hands. They're mirror images, but you can't perfectly superimpose one onto the other.
Right, yeah.
So that's the same kind of idea here.
I'm starting to see how this gets complicated pretty quickly.
Yeah.
We've got these primitive necklaces, and we're treating mirror images as the same.
Yes.
So how do we actually count these unique necklaces? It sounds like we need some serious math firepower here.
We do, and that's where sequence A000046 comes in.
Okay.
So the formula for this sequence might seem a little bit intimidating at first, but it's actually quite elegant.
Okay.
And it involves something called the Möbius function.
The Möbius function.
Which is this powerful tool in number theory that helps us sift through divisors and pinpoint those primitive necklaces.
Okay, you've convinced me about primitive necklaces, but this Möbius function still feels a little bit mysterious to me.
Okay.
Can you break it down a little bit further for me and show us why it's so cool?
Absolutely. So let's take a closer look at that formula.
Okay.
A of n equals the sum over all divisors, d of n of d times A0000 of n over d.
Okay, so we're already bringing in a second sequence here.
Yes, we are.
A000011.
So A000011 is the key here.
Okay.
A000011 is the sequence that counts the number of all possible necklaces with n beads.
Go.
Without worrying about them being primitive or not.
Gotcha.
So think of it as our starting point.
Okay, so A000011 gives us like all the possible necklaces.
Yes.
And then the Möbius function swoops in to refine that count.
Exactly. The Möbius function, denoted as Möbi of d, acts like a sieve.
Okay.
It filters out the necklaces that are made by repeating smaller patterns, leaving us only with the truly unique, the primitive ones.
Okay, I'm starting to get the picture. So for each divisor d of our total number of beads n,
yes,
we calculate this Möbius function
yes,
and use it to adjust the count from
right.
A0000 level 1.
Exactly. It's like a mathematical recipe for finding those unique necklaces.
It's pretty cool.
It is.
And that's just the beginning. What makes this even more fascinating is that the Möbius function itself
yes,
has deep connections to other areas of number theory.
It does.
Particularly prime numbers.
Yes.
And factorization.
Exactly.
Prime numbers, you say. Now, things are getting really interesting. But before we dive into that rabbit hole,
yeah,
I think we need a concrete example to really solidify this concept of primitive necklaces.
Let's do that.
Can we walk through one?
Yeah, the source material provides a great example of 7 equals 8.
Okay.
So we're looking at necklaces with 7 beads.
7 beads, got it.
And of 7 equals 8 tells us that there are 8 unique primitive necklaces
Okay.
you can make with 7 beads.
Okay. 7 beads, 8 unique necklaces.
Remembering that we're treating mirror images as the same.
Yes.
And to get to that number 8, the formula tells us that there are 7 arrangements where the necklace is identical to its mirror image.
Okay, hold on.
Yeah.
Do those arrangements have a special name?
They do.
Because I feel like we're getting into some technical territory here.
We are. They're called Eckerl set partitions, but let's not get bogged down in the terminology.
Okay.
For our purposes, just think of them as ways to arrange the beads so that the necklace looks the same in the mirror.
Okay, that makes sense.
Yeah.
7 necklaces with 7 beads that are the same as their reflections.
Exact.
But we're aiming for 8 unique necklaces. Total, right?
We are.
Where does that last one come from?
That's where the 8th arrangement comes in.
Okay.
And it's special because the necklace and its mirror image are actually distinct. They're like our hands remember, mirror images, but not superimposable.
Okay.
So we call this a chiral pair.
So 7 arrangements that are the same as their reflections, plus 1 unique pair,
Right.
gives us a total of 8 unique primitive necklaces
With 7 beads.
with 7 beads.
Yeah.
Okay. I'm starting to see the power of this 00000046 sequence, but I have a feeling we're just scratching the surface.
You're absolutely right. What's truly exciting is how this sequence connects to other areas of mathematics.
Okay.
For instance, there are other sequences in the OEIS that explore different rules for counting necklaces,
Oh.
like those where we do care about the direction of the beads,
Okay.
or those where we only count necklaces with distinct mirror images.
Whoa, so there's a whole family of necklace sequences out there,
There is.
each with its own unique set of rules and mathematical quirks.
Precisely.
This is blowing my mind. Who knew there was so much mathematical depth hiding within this seemingly simple concept of necklaces?
I know, right?
And we're just getting started.
Yeah.
I can't wait to explore those other necklace sequences and delve deeper into the Möbius function
Yes.
and its connections to prime numbers.
Me too.
But for now, I think we need to pause and let all this information sink in.
I agree. Taking a moment to reflect is always a good thing, especially when we're dealing with such intricate concepts.
Yeah, absolutely. Okay, so we'll be back in just a minute.
Welcome back. We left off talking about the Möbius function.
Yeah, that mysterious Möbius function.
Yeah, and as we touched on earlier, it plays a really crucial role in filtering out those repeating patterns
Right.
and leaving us with only the primitive necklaces.
It's like a mathematical detective,
Yes.
sniffing out the truly original designs.
I like that.
And you mentioned its connection to prime numbers.
Yeah,
Can you elaborate on that a little bit? That sounds intriguing.
absolutely. So remember how we were talking about divisors before?
Uh-huh.
Well, the Möbius function is intimately linked to the prime factorization of a number,
Okay.
meaning how it can be expressed as a product of prime numbers.
Right.
In fact, the Möbius function of a number is 0, unless that number is what we call square free.
Square free. Okay, now you're just throwing fancy math terms at me.
I know.
What does that even mean?
It's not as complicated as it sounds.
Oh,
A square-free number is simply a number that isn't divisible by the square of any prime number.
okay.
So, for example, 10 is square-free
Right.
because its prime factorization is 2 times 5. No squares involved.
Right.
But 12 is not square-free because
Okay.
it's divisible by 4,
Uh-huh.
which is 2 squared.
Gotcha.
Yeah.
So the Möbius function is kind of like a spotlight,
Yes.
shining brightly on those special square-free numbers
Uh-huh.
while ignoring the rest.
Yeah.
But how does that actually help us count necklaces?
Good question. So think of it like this when we're calculating the number of primitive necklaces
Okay.
with a certain number of beads.
Uh-huh.
The Möbius function helps us determine how much each divisor contributes to the final count.
Okay.
It tells us whether we should add
Okay.
or subtract
Gotcha.
the number of necklaces associated with that divisor,
Okay.
based on whether it's square-free or not.
So it's like a mathematical balancing act,
It is.
using the properties of prime numbers and factorization
Yeah.
to make sure we only count the unique necklaces.
That's right.
Pretty clever.
It's a beautiful illustration of how these seemingly abstract concepts, like prime numbers, can have these surprising applications in seemingly unrelated areas, like counting necklace patterns.
It's all connected. That's what I love about mathematics. It's like this intricate web where every concept is somehow linked to every other concept.
Exactly. And speaking of connections,
Oh, yeah?
remember those other necklace sequences we mentioned earlier?
Yeah.
The ones that explore different variations on the rules?
Oh, yeah, those other members of the necklace family.
Yes.
We had those oriented necklaces where direction matters.
Yes.
And those chiral necklaces with distinct mirror images.
Right.
And those acral ones that are the same as their reflection.
Yeah.
Can we delve deeper into those now?
Absolutely. Let's start with those oriented necklaces,
Okay.
which are represented by sequence A00000048.
Okay.
In this case, we're no longer treating a necklace and its flipped version as the same. Imagine the beads have little arrows on them,
Okay.
indicating a specific direction.
Okay, yeah, that definitely adds a whole new layer of complexity.
It does.
I imagine the number of unique necklaces would skyrocket when you factor in direction like that.
Absolutely right.
Yeah.
Then we have sequence A308706,
Okay.
which focuses on chiral necklaces.
Good chiral.
And these are the necklaces where the original and its mirror image are distinct,
Okay.
just like our hands remember left and right.
So these are like the one unique pair we
Yeah.
encountered in the 8 of 7 example.
Right.
The one that wasn't the same as its reflection.
Precisely. And lastly, we have A179781,
Okay.
which counts the acral necklaces,
Cool.
the ones that are indistinguishable from their mirror images.
Okay, so it's like we've got this whole spectrum of necklace types.
We do.
Those where direction matters, those where mirror images are distinct, and those where they're identical.
Uh-huh.
It's fascinating how each variation leads to a different mathematical sequence.
It really is. And what's even more amazing is that A00000046,
Okay.
our sequence for primitive necklaces where we don't distinguish between mirror images,
Mm-hmm.
is intimately related to all of these other sequences.
Whoa.
It's like a mathematical Rosetta Stone,
Oh, wow.
helping us understand and connect these different ways of counting necklaces.
That's really cool.
It is.
It sounds like 800000046 is the key to unlocking the secrets of this entire necklace counting world.
I think so.
We've uncovered so much already. Divisors, prime numbers,
Yeah.
this Möbius function,
The Möbius function.
and this whole family of necklace sequences.
Yeah, it's a lot.
And I can't help but wonder, are there even more connections out there waiting to be discovered?
Who knows?
Perhaps in other branches of mathematics?
Possibly.
Or even in unexpected real-world applications?
That's the beauty of exploration. There's always more to learn, more connections to uncover, and who knows, maybe we'll stumble upon something truly groundbreaking along the way.
Welcome back to the Deep Dive. We've been on this incredible mathematical journey, exploring these fascinating primitive necklaces and all the intricate concepts behind them.
It is pretty wild, isn't it?
I know, right? It's amazing. We talked about divisors and prime numbers and this mysterious Möbius function.
Yeah.
We even ventured into like a whole family of necklace sequences,
A whole family.
each with its own little set of rules.
Yeah, they all have their own personalities.
Yeah, exactly. But I'm curious, are there any practical applications for all this? I mean, besides,
Yeah.
satisfying our inner math geek, of course.
Right. Well, it might surprise you to learn that these concepts do have some real-world applications,
Okay.
particularly in areas like cryptography.
Cryptography.
Yeah.
Like codes and ciphers.
Yeah, exactly.
How does necklace counting fit into that world?
Well, it turns out that the same mathematical principles that we've been talking about can be used to design and analyze error-correcting codes.
Error-correcting codes.
Yeah.
Okay.
And these codes are actually essential in all of our modern communication systems.
Really?
Yeah, to make sure that data is transmitted reliably,
Wow.
even if there's noise or interference.
So you're telling me that the same math we use to count these unique necklaces helps ensure that, like, my text messages and emails get delivered without errors.
Yes,
That's pretty mind-blowing.
it is, isn't it? The idea is that we can represent data as sequences, kind of like beads on a necklace.
Okay.
And by using these really sophisticated mathematical tools
Okay.
that were inspired by these necklace counting techniques,
Yeah.
we can create codes that can detect and correct errors that might occur during transmission.
So it's like those error-correcting codes are
Yeah.
wearing, like, mathematical armor,
That's a great way to think about it.
protecting our data from getting scrambled.
Exactly.
Wow. I never would have guessed that such abstract concepts could have such a direct impact on our, everyday lives.
That's the beauty of mathematics. It often operates behind the scenes, subtly shaping the technologies and systems that we rely on without us even realizing it.
Yeah, that's so true. It really is amazing. And who knows what other applications might be waiting to be discovered, right?
Right, exactly. It makes you wonder.
Yeah, it really does. So to all our listeners out there, as we wrap up our deep dives into this world of A00000046
Yeah.
and all of its fascinating relatives, I hope you're leaving with a newfound appreciation for this power and beauty of number theory.
It's pretty amazing.
It is. It's not just about, these abstract concepts and formulas. It's a vibrant field with connections to countless other areas of mathematics and even, the technologies we use every day.
Absolutely couldn't have said it better myself. The world of mathematics is full of surprises, and oftentimes the most unexpected discoveries are the most rewarding.
That is so true. So keep exploring, keep asking those questions, and never stop being curious about the world around you. You never know what mathematical marvels you might uncover. Until next time, happy counting.